Okay, let's keep talking about flux. Again, the idea of flux is that it will measure how much of fluid is escaping or entering through a surface, or how fluid is moving through a surface. Here was the official definition of flux. You have a vector field, which you think as the velocity of the fluid, and you only care, the part that's escaping or entering has to do only with the component of the vector field which is normal to the surface, so that's why you take the dot product with the normal vector to the surface, and then you integrate this. So what I would do is compute the flux for this vector field through the cylinder, y squared plus z squared equals 9, x equals 0, x equals 2. So how should you think of this cylinder? Notice that this is a little bit different from the cylinders from before, because it's not like x squared plus y squared equals 9, but it's still the same idea. So here's x, y, c, and so the cylinder is on the yz plane, so it's something like this, and then you have to imagine that the x-axis is facing you, so really you have to move this circle along the x-axis, and you get the cylinder that I care about. And so essentially this is a cylinder, so there are three surfaces that we will consider for this problem. One which you can think of as the top surface, another which you can think of as a bottom surface, and like another one which is like the lateral surface, which is this pink one, like the actual cylindrical part of the cylinder. And so what I'm trying to say is, again, flux is additive, so you can break the flux for each of the pieces. So the flux through the entire surface S will be the flux through the top surface plus the flux through the bottom surface plus the flux through the, let's call the other Z for cylindrical, through the cylindrical surface. Okay, and as usual, you can think of this cylinder as a can of Coca-Cola or something like that. So it's a cylinder. The normal vector, remember that there are always two choices of normal vectors to any surface, because you can always flip it around. And so for these problems, and I'll tell the convention more precisely later, but usually you choose the normal vectors that point away from the interior of the cylinder. So meaning that there's like a normal vector here that's pointing away from the cylinder, there's another normal vector here that's pointing away from the cylinder, and then there's another normal vector that's pointing away from the cylinder. So n points away from the region enclosed by the cylinder. And so now let's start with top and bottom, because those are the easiest to compute. So let's find, again, this is a definition, official definition for the flux. So what's the flux along the top part? Well, it's a surface integral of f dot n. Let's call it top. The S. But what is a norm? So again, the top here is like, the surface is like, the part that we're considering right now is like a disk. And the normal vector is a normal vector perpendicular to this disk. It's just pointing along the x-axis. And so the normal vector really is the vector I. And so when you do the dot product between f and I, the only thing that survives is this term. So you get 2x squared y ds. And now the question is how to integrate ds. And again, well, here you can just do like polar coordinates because this is basically perfectly aligned to the yz plane. And so you can just say you're using like polar coordinates. Oh, yeah. Let's see. Along the top part, right? The top part is characterized by x equals 2. So here is x equals 2. So this is 2 so x equals 2 on the top part. So you can actually simplify this a little bit more before doing the actual integral. You can say that this is the integral over the top piece of 2 times 4 times y ds. And so this is just the integral over the top piece of 8 times y ds. And now here's where I'm going to use polar coordinates, but the polar coordinates that I'm doing are really like polar coordinates for yz. So y is like r cosine of theta, and z equals r sine of theta. And the s is really the a in this case. So you're doing y, which is replaced with r cosine of theta, and then ds becomes r dr d theta. Okay? And this will go from 0 to 2 pi, and this is a cylinder of radius 3, so this is going from 0 to 3. Okay? And I think, well, this definition of flux is not too difficult to memorize, so let me erase it here so that we can work on an additional board. So what we find is that the integral is equal to 8, 0 to 2 pi. Well, the integral of r squared does, well, the cosine of theta is still cosine of theta. The integral of r squared is r cubed over 3, from 0 to 3, d theta. So this is 27 over 3, that's 9. And this is, well, the 72 times negative, sine of theta at theta equals 2 pi, and theta equals 0, and that will give you 0. So in that case, this means that really there is no flux through this component. So I mean, that could mean that some particles are escaping and others are entering, and so on the net there's nothing like happening through this top piece. So the top piece is 0. Let's go over the bottom piece. So the bottom piece again is the integral of over the bottom piece of over the bottom piece of f with the normal vector. As I was saying, the normal vector, we're taking it to be pointing away from the interior of the cylinder. So really, now the normal vector is minus I. And so you get, again, another time you get minus the integral over the bottom piece of what survives here is 2x squared y ds. But now over the bottom piece, right, the bottom piece is x equals 0. So this piece equals 0 here. And so you get 0 altogether because this just went away. So you get 0. As well. And finally, we have to worry about the cylindrical piece, so that the lateral piece. Let's see. Yeah. Okay. Let's do the cylindrical piece here. Even before computing the flux, we will need a formula for ds in this case. So in order to find that formula, we have to parameterize first that piece of the cylinder. As I was saying, we want to use like polar coordinates or cylindrical coordinates. But now x is like playing the role of z, so because we have reversed a little bit what's going on. So x is like x, y is r cosine of theta, and z equals r sine of theta. So notice I'm doing cylindrical coordinates, but with the roles of the variables interchanged a little bit. And so a point on this cylindrical piece is of the form x, y, z, which will become x, r cosine of theta, r sine of theta. But the point of belonging to the cylinder, if you write this equation in these new cylindrical coordinates, this gives you that r equals 3. So the parameterization for a point on the cylinder is in terms of x and theta, and that is the form x 3 cosine of theta, 3 sine of theta. And now, once we know this, remember that you have to find the partial derivatives of this position vector with respect to the two variables. You get this. And ds, if you remember, is the norm of the cross product of these two vectors. So let's think first about what the cross product is. And let's see. So it's I, J, K, 1, 0, 0, 0, negative 3 sine of theta, 3 cosine of theta. Okay, and so it gives you the following. It gives you, it gives you 0, right? Yeah. And then it gives you negative 3 cosine of theta, and then it gives you negative 3 sine of theta. So remember that this basically works almost as a normal vector. If you think about it, the fact that it has negative signs means that it's pointing towards the x-axis, like towards the origin. And so the normal vector, the norm of this thing, so ds. Okay, let's do it here. So what I'm trying to say is that ds was just the norm of this quantity times dx d theta, and so it would just be the norm of this is 3 dx d theta, and then the normal vector has to be, this has to be normalized. When the norm is 3, so you just divide by 3 and that's fine. But the normal vector that you actually have to use is the one that's pointing away from the cylinder, so you have to change the signs a little bit. Okay? And so, well, yeah. And now we should be able to compute the flux. So the flux along the cylindrical piece will be the integral from 0 to 2 pi from 0 to 3 of f dot n ds. I'm getting ahead of myself. The ds will be 3 dx d theta. Oh yeah, 3 dx d theta. So theta will be from 0 to 2 pi, and x will be from 0 to 2, not 0 to 3, sorry. So this will be the integral from 0 to 2 pi, 0 to 2. What's the dot product between these vectors? Well, now you don't care about the first component, and so you only do minus, the normal vector should not have 3 because it's unit norm. Okay, so it would be cosine minus y squared cosine of theta plus 4x z squared times sine of theta dx d theta. But then you have to remember that on the cylinder y equals there's a 3 that I forgot here. You have to remember that on the cylinder y equals 3 cosine of theta and z equals 3 sine of theta, so you get the integral from 0 to 2 pi from 0 to 2 of what? You get so when you put y as 3 cosine, you get negative 9 cosine cube of theta, and here you get 4x. This becomes 9 sine cube of theta. So this 4 times 9 becomes 36. So you get 36x sine cube of theta, and this is being multiplied times 3 dx d theta. Okay. And so let's see. Okay, this is making sense. Yeah. Oh, okay, yeah. Okay, let's see. Okay, good. So when you integrate from 0 to 2 pi, you do the integral from 0 to 2 pi, this just becomes negative 18 cosine, so 3 times the integral from 0 to 2 pi, negative 18 cosine cube of theta, plus when you integrate x, you get x squared over 2, evaluated at 2 and 0, that gives you just 2, so you get plus 72 sine cube of theta d theta. But then each of these is 0. This one is 0 because you're integrating from 0 to 2 pi an odd function, and this one is 0 if you use the fact that cosine cube is cosine times cosine squared, which is 1 minus sine squared, and then you can check that that integral is 0 as well. And so the point is that this will be 0. And the whole idea of Gauss's theorem, which I'll explain next time, is that you don't have to do all this mess, and instead of computing these 3 separate integrals, you can just compute a single triple integral.